This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
Hello, this is Charles Anderson for Software Engineering Radio. Today we are talking to James Phillips from Hoshi Corp. At Hoshi Corp, James works on Consul and Surf. He also developed fault-tolerant avionics for SpaceX and called out flight software is go during the first SpaceX missions to the ISS. He has also worked on web applications and embedded systems. Today we will be talking to him about service discovery. Welcome to Software Engineering Radio, James.
Thanks for having me on the podcast. It's good to be here. I do have a bit of an odd mix in my background of sort of embedded things and web applications, but I think it was good training for what I do at HashiCorp with real-time mixed with distributed systems.
Great. So why don't we dive in then? So can you tell us at a very high level, what is service discovery?
So at the highest level, it's basically a system that lets you say, where is service foo? And that answer is usually something in the form of an IP address and a port number. And a service can be kind of a logical entity within your architecture. So you might have, a database, or you might have a pool of application servers, things like that. So usually there's a set of processes that back a given service. And usually for most highly available things or scalable things, there's more than one process that makes up a service. And service discovery lets you find those things on kind of a spectrum of maybe you could have a fully statically configured service discovery system or a very, very dynamic service discovery system. So the techniques you use to do service discovery vary a lot, depending mostly on sort of how fresh the information is and how changes get put into your service discovery catalog.
So when you say a very static configuration, that makes me think of just using configuration files where I might update them occasionally, and I could use a configuration management tool like Puppet or Chef. What's wrong with that approach?
That approach can work okay when you have a small handful of things you manage, but as soon as you get even sort of a largish, medium, largish to very large infrastructure, it becomes very, very hard to keep that catalog up to date by hand. The times involved to do a convergence run can, run into minutes. That's often not fast enough to propagate a change. And also just having a human in the loop to sort of check in changes to that catalog, manage a list of IPs, and then have a system push that out becomes a burden in a system that, you want to run as automatically as possible. So it becomes kind of a maintenance burden and a response time problem for an infrastructure. Once it gets beyond once it's beyond sort of a trivial scale, that gets really, really hard to manage.
Right. And I can imagine even at a small scale, you mentioned response time. If you need response time, it's still going to take a while.
Yeah. If your database, if you do a master failover and you want to point all your clients at somewhere else, you want that change to go out quickly. You don't want that to take, tens of minutes to propagate through your system. So the configuration management tools definitely have a role. Even if you're using a service discovery system for bootstrapping new nodes or kind of getting the service discovery system kicked off. But in terms of managing sort of the ongoing state of your infrastructure, it becomes very, very difficult to do with a sort of a static setup.
Okay. We've been talking about scale. That kind of hints to kind of larger networks. What network scope is appropriate for service discovery? Sort of LAN, data center, cross data centers?
My short answer to that is yes. It can have a place basically at all those different sort of levels. So, within an application, you wouldn't necessarily have it, within a process. You're not going to find like components or plugins with a service discovery mechanism. But once you have a process trying to find out where another process is, it's appropriate there. And then when you get into highly available or globally distributed infrastructures, it definitely makes sense for, some service in data center A to reach out and find an instance of another service in data center B. So it makes sense, Usually there's sort of a preferential scope. You want to use things that are close and nearby. And then as, sometimes it's part of normal operations to find things remotely or, at a much larger tier across the internet. And it definitely makes sense when you're talking about, geo redundancy and failover and things like that. So you want, ideally, your service discovery system would let you cross those boundaries without having to have like a totally separate instance that's totally disconnected and your application has to know about how to go reach out to all these different things.
Okay. In a local network, would service discovery be comparable to the zero configuration networking, something like the Apple Bonjour? Is that a form of service discovery?
It definitely is, in terms of sort of the most basic, what's the IP report of an instance of this type of service? We'll see later, there's other facets of service discovery, like managing other types of configuration or orchestration, where something like that probably isn't ideal. And it's also a system that often requires dependence on things like multicast and features like that. So that's like sort of a low-level piece that might be part of a bigger service discovery solution if you look at sort of a full spectrum of what you need in a complete solution. But it'd be a very limited form of service discovery.
So you mentioned processes finding one another. Can you tell us some more about some scenarios where service discovery would be appropriate? When you talk about processes finding each other, I think of something like a service-oriented architecture, possibly microservices.
Definitely. Service discovery, I think even for a monolithic application, your basic configuration, like where's the database? How do I connect to it? That even makes sense in that type of architecture. But as you move to service-oriented or microservices, you're going to have sort of a much more distributed set of pieces that need to find each other. You'll have much more sort of dynamic environment in terms of different pieces of your architecture coming and going over time. In general, you'll have more than one instance to choose from. So you'll want to choose a healthy one to talk to. So the things get a lot more dynamic as you have an architecture that's distributed across more sort of functional pieces. So service discovery really shines there. And then in the extreme, if you're running under a resource scheduler like Kubernetes or Mesos or Nomad, you'll have your pieces are placed onto machines in your cluster basically by an automated infrastructure. So at that point, there's basically no chance to have, humans editing config files and pushing out changes. You need something that in real time can manage where all your resources are and which ones are healthy and where to find them.
Okay. Are there applications or scenarios where I wouldn't want to use service discovery?
I don't think so. I think the basic sort of hygiene of separating the configuration out of your application is a good thing to start with early on. You don't want to be hard coding IP addresses, in your source code or whatever in the extreme. So you're going to want some separation there from the beginning. And I think it's also easy to sort of progressively use different features of service discovery mechanisms as your application gets more sophisticated. So with a service discovery system that supports a DNS interface, you can use service discovery by just having your application look up a host name. So you can have like essentially a zero-touch integration even very early on. And then over time, you might need to use orchestration features to elect a leader among many potential leaders in your pool of services, things like that. So it's possible to sort of start simple with an integration that's very, very lightweight or essentially even zero impact your application code, and then expand from there. But to start that way versus hard coding or maintaining these things is a good way to go. And also, in a world where you might be building AMIs and machine images and things like that, it's a nice like separating out the service discovery piece into a separate layer is handy for not having to bake a new AMI when some configuration changes. So having that layer in there can even have practical implications for your deployment pipeline and just how you manage your images for deployment.
Okay, so yeah, you said something there that made me think about immutable infrastructure, and certainly if you're talking about baked in AMIs and actually extracting out this variable configuration and information, that would make sense, right?
Yeah. And having that layer there and then being able to dynamically push changes out after something's deployed without having to actually, invasively get into that image and change its configuration is a super big plus. And that same AMI can connect to any database or connect to any instance of your API server or whatnot, because it's getting all that configuration on the fly from the service discovery system.
Okay, so move at least the configuration related variability out of your infrastructure. All right, that makes sense. Let's move into some more kind of technical details. What data are typically stored in service discovery repositories? You mentioned host names or IPs and port numbers. Is that kind of the extent of it, or is there more?
That's sort of the most fundamental data, but when you get into managing services their configuration, you generally need a little bit more information. So you'll typically have things like database username, potentially credentials, tokens, like other configuration type information that goes along with the basic IP and port information that's already stored in the service discovery system. It's also a good place to put things like feature flags. There's kind of a general bucket of key value information that nearly every service discovery system supports, which is useful for capturing basically the whole set of configuration data that you might need for interacting with other services.
Okay, yeah, I was going to ask about something like database credentials or something. So those could be in service discovery. And then I hadn't even thought of feature flags. So what are you mentioned kind of a key value storage thing. What are typical components of a service discovery tool?
So the sort of, if you want to take a complete solution for service discovery, it really comes down to 4 different pieces. So there's the core service discovery. So, where is this thing? What's its IP and port? How do I connect to it? Any complete solution generally needs a health monitoring piece. It's not really interesting to get an instance that's no longer functioning when you're looking for something to connect to. So having a health monitoring component creates a really sort of fresh and live set of data that's going to be very easy to manage in your infrastructure. You need some configuration storage. So that's generally in the form of a KV store, key value store, and that can also be used for coordination. So we can talk about some applications around that. And then an orchestration piece. So it's often useful to be able to say, among many possible instances, help have tools to elect a leader or make sure that a certain operation is done in a way that doesn't have any race conditions. Or even some systems even let you do things like send events out or run commands, do like sort of more dynamic things if you want to have an event go out across your fleet and cause some action to happen, things like that.
Okay. Would load balancing be a function of service discovery, or is that going to be something separate?
It can be, and it's sort of an architectural choice with different service discovery systems. So some sort of make load balancing first class part of the architecture. So you'll route all your traffic, get some kind of load balancer, and then that'll manage talking to the different healthy instances. It's often the case, though, where you can actually avoid load balancing with the service discovery system and avoid that whole tier and potential point of failure. So if you can talk directly to a healthy instance by virtue of how your service discovery system works, it's actually kind of nice to avoid load balancing if you can. Like there's different trade-offs and there's different choices. One common thing is sort of within your data center, you might not use load balancers at all, and you'll use your service discovery system to manage handing out here's a healthy instance of this service, talk to this guy, and if it fails, you can get a new one. But then you'll use your service discovery system to configure an external load balancer that your customers are using, say like that your website IP addresses are pointed to, so that you can have combinations of things. And some systems run load balancers internally that route traffic over overlay networks and things like that. So there's quite a range of different solutions there.
Okay, so how do servers that want to offer a service, how do they know where they're going to register to? And on the flip side of that, the clients that are looking for a service, how do they know? I mean, do we need another layer of service discovery?
Yeah, I think it'd be turtles. Yeah, it's sort of turtles all the way down for service discovery. You generally need some kind of seed or some way to introduce a new entity into the service discovery system. Some systems do that with, some well-known DNS, some serve records for some, root servers to talk to. HashiCorp's Consul has a Atlas join feature, so we actually have a free sort of hosted joining service that'll help you find other nodes to talk to initially. And there's also different architectures in terms of how you access the service discovery system. Consul, for example, runs an agent on every node, so your applications only ever talk to their local agent, and the Consul kind of manages how to talk to servers and how to route your requests around. Other systems, you might have to locate sort of a central server and make requests against that. So there's different strategies, but there usually is some sort of bootstrapping process or service that you need to kick things off.
Okay, yeah, that makes sense. You said seed, and at some point in time, all the way down to following all the turtles down, we hit an egg or a seed there.
Yeah, there's maybe a hard-coded IP address or something similar somewhere, but there's things like Atlas Join make that pretty easy. Like you can have a well-known thing to reach out to, and it'll manage finding you a server to join with.
Okay, yeah, I want to touch on Atlas towards the end here, but in the meantime, given that service discovery, the way we've been talking about it, it's going to be used possibly by pretty much the whole app, even trying to find the database and things like that. It's going to need to be fairly reliable. What are some features or characteristics of service discovery tools that provide the reliability?
Yeah, that's definitely a prime concern for a system like this, which could potentially be it'd be sort of like a nuclear single point of failure if it wasn't done properly. So a key component of nearly any any service discovery system is to be distributed and replicated. So you need to be able to basically build out redundancy to whatever level of failure tolerance you want. And that may mean having redundancy within your, say, kind of a local area network kind of scope. So you might have multiple servers. And then you may also want redundancy by having sort of different federations of servers that can talk to each other and might be in different geographic locations and things like that. So having a distributed system with replication that can handle, a server going completely offline or two servers or whatever level you want to provision to is very important. And then there's also the concerns of dealing with, what happens when the system is down altogether. So in the event of a partition or something like that, there's different strategies for, say like if you had a system that has a consensus algorithm and requires a certain number of servers for a quorum. And if you get below that number of servers, so maybe you can't make writes to your system anymore, you can't make any changes, you still want the reads to work well. So there's tools that are exposed to the clients to say, hey, I'm willing to take some stale information. I just want to, what's your best information that you had as of, this long ago or whatnot. So you want it to operate even in sort of degraded modes and fail gracefully. And kind of at a very practical level, there's a lot of sort of techniques that good service discovery solutions have in terms of, managing how they deal with retries and how they avoid thundering herds when things come back online. How do they randomize traffic to spread load among different components? How do you scale certain events based on the size of the clusters and things like that? So there's quite a bit of layers that go into making a robust service discovery system that's going to keep working no matter what.
Okay. And when you say distributed system, we mean sort of in the classic sense of 3 or 5 or 7 servers, and you mentioned a consensus algorithm possibly. And so then that kind of would get us into the CAP theorem, for example, right? In terms of making some decisions or trade-offs there.
Yes, and there's definitely the different tools have different strategies and different trade-offs, and there are AP type systems, and they have that we can give some examples of specifics, but there are systems that make sort of more of an AP sort of bent that will have better availability, but potentially much harder to reason about failure modes, where you might end up with, two different sides of your cluster working in two different ways. And then there are systems that go more the CP route. So those are often easier to reason about, I think, for operators, and they have a consensus algorithm that lets you kind of know the state of your cluster and have a known behavior in the event that things go wrong. That's fairly easy to reason about. So there's different, kind of depending on your application, there's different considerations, but I would say most systems tend towards a CP type architecture.
So preferring consistency and partition tolerance over availability?
Yeah, but with the caveat that you have sort of a read level of availability, even in the loss of a loss of quorum, say. So you need to think about that case and not have it just knock out. But the minority that can't make progress in terms of making writes can still read the current state as it was at the time the partition happened, for example.
Okay, yeah, that makes sense. We've mentioned a couple of times about databases. Suppose, rather than running my own database server, I'm hosting in Amazon AWS and I'm using their service for RDS to provide my MySQL or Postgres server. Would I still be using service discovery to discover the database, even though in theory Amazon's going to keep it pretty stable for me?
I think so, because tools like Consul have support for what we call external services. So those are static registrations, but they are served in the same manner in terms of Consul's APIs as any other service.
Okay, so yeah, consistency. So you're not special casing Amazon.
That's right. So you can manage it sort of in the same place. You could retrieve it in the same way. And then if you were going to, manage some portion of your database infrastructure yourself, it'll sort of nicely ramp into being supported by Consul without changing your clients. So it's like getting that sort of basic hygiene of having all your configuration in one place. You can definitely do that with external services.
Right. And it also gives you the flexibility then, if everyone's using the same pattern, to make different decisions in the future.
That's right. And the overhead is pretty low. I mean, it's one level of indirection, which software engineers are always okay with. Just one more level of indirection.
One more level and we can solve any problem.
That's right.
So how important is security in a service discovery tool? Do we need to use cryptography either to encrypt the communications or authenticating clients and servers?
Security is pretty huge. I mean, this system basically will direct your internal services to connect to things and make requests to them. It could be key to finding, where the database is. You could potentially have credentials in there. So yeah, any actual production deployment of a service discovery system needs to think about security. Generally people use TLS to secure all the traffic. It's usually important to verify the identity of your servers. So you can also use, certificate verification. Like you don't want sort of random nodes on your network joining on as servers and potentially interfering with the quorum or, a rogue amount that can push bad data in there, things like that. And then on top of sort of the basic transport level stuff, most tools also involve some layer of access control type tools available within the service discovery system itself. So you can scope who's going to be able to, create new entries, who can delete things, who can update key values, which, you can segment your paths to where different parts of your organization can kind of self-manage different parts of your service discovery system. Okay.
And then I would also think it probably depends or could depend on kind of the scope of the network that you're using. If we're just talking about a local area network or a rack on premises, that might be different than if you were talking about a number of nodes trying to find each other on Amazon.
It could be, yeah. I mean, it definitely, different practices might make sense in different ways at sort of different levels of organization, things like that. But it's generally good to start with TLS and some of the basics in there, and then you might only start creating ACL policies once your organization gets complex, or you get a couple different teams using the same service discovery system. So some of that can evolve, but it's good to have just sort of a basic level of transport security underneath as a sort of I just call that sort of like a baseline setup.
Okay. You've mentioned Consul as a service discovery tool, and obviously, I mean, you work on it. And we'll discuss that in a moment. But what are some of the other tools that are out there in this space that you know of? I don't expect you to be an expert on any or all of them, and we certainly don't have time to dive into them. But just for other tools that listeners might be interested in.
Sure. And I'm definitely, I'm not an expert in every service discovery system out there. I do work on Consul full time, so that's where I know the most. But there's a class of tools that I would roughly kind of lump into sort of key value stores. So like Zookeeper, etcd, Doozer, and Consul actually has a key value store as well. And these sort of generally provide kind of a highly available key value store that can be accessed by clients. And they often include mechanisms like coordination, so locking type features. So you can have you can actually coordinate around a key and make sure that value updates are atomic. They generally include some kind of health checking notion too, where a client will maintain a connection, and if the connection closes, something can happen in the key value store. So you can kind of know that, there's some notion of some client being alive, and a way to have the servers help manage that. And then these generally couple some type of consensus algorithm to provide a distributed replicated key store. So the main thing that differentiates these different solutions, and where Consul is a little bit unique, is these often I think of as kind of like lower level toolkits. So you can build service discovery systems on top of these, but they don't necessarily have maybe as deep a mapping of all the service discovery concepts in a form that's easy to use. So they're kind of like a building block piece, but not necessarily a full solution. So like they might have basic health checking in the form of monitoring a TCP connection, or having like a check-in kind of thing with a central server, but you wouldn't be able to do more general health checking things like running a Nagios script or something like that. And they often don't handle some of the sort of more global scales we talked about, like spanning different geographic regions and things like that. That's generally left to be sort of something that a client manages. So a full sort of service discovery solution, I think, would encompass more than most of the sort of basic key value stores have, but they're, as sort of a building block, they're capable of doing pretty powerful service discovery type things.
Yeah, we talked about in episode 229 of the podcast, we talked about Zookeeper. And yeah, it was more on the level of the key value store and coordination algorithms and whatnot, rather than high level things like service discovery.
Yeah. And there's other solutions. There's things like SkyDNS. So it is sort of a DNS-centric system that's backed by a consistent distributed system under the hood to manage the failure tolerance. SkyDNS and Consul both have a DNS interface, which makes it really easy to integrate with your existing applications with essentially no modifications. So you don't have to do a deep sort of client integration. You just look up a host and get ports from server records and things like that. So there's different features in these different products, but SkyDNS is one, and Consul has a DNS interface. And then there's more. There's others that are sort of more unique, kind of hybrid solutions, like SmartStack sort of composes several different pieces, and it uses Zookeeper under the hood, and it actually uses Zookeeper for sort of its consistent database, and then it uses HA proxy as its load balancing layer and kind of manages all those pieces together for you. So it's kind of a unique architecture that has, I'd say it's a little more complicated, but it has like a very specific opinion about, you're going to use a load balancer, I'm going to manage the load balancer for you. And then it composes several pieces around that. And there's things like Eureka from Netflix, which actually has sort of more of an AP sort of style to it. And it has some of the pieces of the basic like find me an IP and port, it has less of the coordination sort of general KV store type features. So it's a different mix. And all these have different health checking strategies. There's a different mix of sort of basic interface type things. Like some have thicker clients, some have really lightweight clients, some have zero clients like DNS interfaces. So among all these, there are many different types of architectures. Most solutions, though, I would say cover something on the order of 1/5 to 3/5 of what I would consider kind of an ideal scope for a full service discovery solution, though. So many of these tools, they'll do one part really well, but they require you to build to get, better health checking, or you might have really good knowledge of where services are with IP and ports, things like that, but you don't have a KV store, so you'd have to use something else there. So most of these would require you to compose several things together to get a complete solution.
Okay. So speaking of complete solutions, perhaps we can then dive into your wheelhouse, so to speak, and talk about Consul. So Consul is an open source service discovery tool from Hoshi Corp, where you work. At a high level, what features does it provide? I mean, you were just discussing kind of trade-offs, or how different applications have different sets of things that they're bringing. What does Consul bring?
Yeah, I think Consul's unique, and I think it grew out of experience. We had an earlier project which we still use, and is sort of the one of the basic layers that Consul's built on, called Surf. Surf was an AP system that is used to maintain kind of a basic list of members in a cluster with some additional metadata on them, and to do some health checking. We'll talk a little bit about how that fits in, but in the experience with building Surf and thinking about, what do operators have to reason about? What should a service discovery system really, integrate together to do well? A Consul grew out of that. And it really comes down to 4 different pieces. So the basic service discovery piece that we've talked about, Consul focuses on that, but ties it to things like health monitoring, which is our second key component, at a deep level. So it's nice to have a good catalog, but if the catalog's out of date, then it's not that useful. So by coupling the service discovery engine with a really rich health monitoring engine, you have a much more powerful service discovery system. And that's a set of tools you can just use out of the box. So discovery, health monitoring, configuration, I mentioned before, like many of the systems include a KV store. That's a key part of Consul as well. And we can talk about this in detail too. Even our configuration store is tied in with our health monitoring store, which means it's tied in with service discovery. And then the final piece is orchestration. So the ability to coordinate with your service discovery system, the ability to send events and kind of manage your cluster in real time, that's another key component of Consul. So tying all those 4 pieces together is really what makes Consul kind of stand out from the rest. It's got all those things sort of thoughtfully integrated in a way that's really easy to use, and that will do most of what people want right out of the box.
Okay. What's kind of the basic architecture? You mentioned agents and communicating with servers.
Sure. So yeah, the basic architecture of Consul is that you run the Consul agent on every node in your cluster. So it's basically a single Go binary in CC to deploy, and that runs everywhere. And then you'll have some subset of your nodes that are servers. So you'll usually have like 3 or 5, depending on your failure tolerance. 3 can handle 1 server failure, 5 can handle 2. So they run the same agent, but it's in a different mode. It's in server mode. So each node is running an agent. Service registration and health checks and all those basic functions about what's going on a given node actually happen with the agent on the node. And then that agent syncs the information back to the servers. And the servers run the raft consensus algorithm to apply changes in a consistent way to a state store. So it's a little unusual, and it's something most people don't appreciate at first glance, but the agents are actually the source of truth for all your service configuration information. The servers manage a central copy of that, which is the catalog, and then they also manage things that are sort of information that belong to the whole cluster, like the KV store and your ACLs and things like that. So if you were to, say, swap out your servers, eventually, once the servers come back online, the agents will sync their service configuration back up with the catalog, and you'll be off and running. So it's kind of an interesting division of labor.
So all of the agents have the full key value store?
They don't. So the agents have their configuration for their node's services, and when you request or make a change to the key value store or request a key, those actually are requests that are forwarded up to the servers.
Okay, so they are managing truth for their local node.
Yes.
Okay.
And they're syncing that truth back up with the servers, and then the servers maintain basically a central copy of that truth as well as the key value store. So that's managed centrally by the servers.
Okay. Then what protocols does Consul support for either the service that's starting up that wants to say I'm available, or the client that says I need to find this service? I believe you mentioned DNS as one option.
That is one option. So yeah, so once you have the agent running, and you can configure different, you can disable these or enable these as appropriate. The two main interfaces for talking to it are the DNS interface and an HTTP API. And generally, you'll run the agent on your local node, and you'll have your applications always just talk to localhost port 8500. So your applications will always just talk to Consul using their local node's agent interfaces. And then behind the scenes, that agent is keeping track of where the Consul servers are. If a server comes and goes, it'll put it on the list to, it'll manage that list of servers that are possible. If a client uses the HTTP API to, say, read a KV entry, the local agent will forward a request up to the server and route the information back and serve it to the client. So the clients always just talk to localhost essentially, and they can do it over HTTP or DNS.
Okay, but if a server's publishing, saying I'm here and available, that wouldn't be over DNS, right?
That would not.
Okay.
So underlying the Consul system, we mentioned Surf is sort of under the hood there. So as sort of a background process, each Consul agent does a periodic ping of another random agent, as well as an exchange of gossip information. So there's a underlying technology that's based on an academic paper. It's called SWIM, but there's a gossip protocol that's kind of a low-level part of Consul. So, for example, when you join a new node, you need basically only the address of one other node, and you'll talk to that one, learn about the other nodes in the cluster, and then start participating in gossip and the random probing to check for the aliveness of the other nodes. So that's a mechanism that your agent on a given node will use to it'll discover that another server came online, for example, through that process. And that's that's like a low-level part of Consul's architecture. It's extremely powerful because the gossip layer provides a built-in distributed failure detector. So Consul's constantly checking the health of all the nodes in the cluster and maintaining membership information about nodes that are coming and going. And the nice thing about SWIM is that's done in a way that basically has kind of a low volume, constant level of traffic that scales nicely across the cluster. So it's not, some n squared kind of thing. It's a constant level where, at each interval, each node will pick one other random node to probe. And then there's a gossip propagation mechanism to get the information around nodes coming and going around the cluster. So there's sort of an AP underpinning to Consul that provides this information of, which servers are available. This node is no longer functioning. That's kind of a low level of traffic that Consul maintains automatically.
So it's maintaining CP, or you said AP, but then Consul's service itself, is that AP or is that more CP? I think you said previously.
The events of, say, a node coming or a node being declared dead, those propagate through the gossip layer in sort of an AP fashion. And then as those events are recognized by the servers, they get fed into the catalog in a consistent fashion. So when you do service discovery and you say, give me a healthy instance of this service, that's actually a request that's going up to the servers and being done based on the consistent view of the cluster. But there's a low level sort of AP view of the cluster that's being constantly maintained and updated by all the nodes, in particular the distributed failure detector. So the nodes are checking each other and then reporting that information back up, and then the servers feed that into the catalog using the consensus algorithm. So your view of the cluster is always through kind of a lens of this consistent catalog, but the underlying mechanism that helps realize that view and provide the events of this node just joined, this one went away, is happening by this gossip protocol under the hood.
Okay, so that explains sort of the confusion, is that there are at least two distinct layers and they are aligning themselves differently on the cap triangle, so to speak.
Yeah, this is a really good place for a diagram, but verbally it's kind of a, you can almost think of the surf layer is kind of it's sort of a layer that informs the consistent layer, but the consistent layer is what you use for actually doing the service discovery. So it's kind of like a transport mechanism, but I don't want to create more confusion there. But it's a way to move events around or say or announce that, hey, this server just joined, or this server is no longer healthy. I don't think we should be using the services that were on it anymore. Things like that.
Okay, if I've got an application and it wants to find services and whatnot, and we talked about doing that through DNS or HTTP. But if I've got experience with Ruby on Rails where we've got a whole bunch of YML files. Do I need to rewrite my application in terms of how it's configuring itself instead of using YML files, or to do DNS or HTTP, or is there another option?
There is, and it's very common to do this. So any application that is driven by configuration files, we have some tools, and there are other community tools. Two in particular, there's something called Consul template, and there's another one called env Consul, and those are both HashiCorp tools. And what those do is you'll run a process on a given node. It'll make a kind of a blocking long pole request up to the Consul servers to watch for things to change. And whenever a change is made to the configuration, they'll render a new config file from a template, in the case of Consul template, or in the case of env Consul, they'll restart an application and set environment variables with configuration variables that came from Consul, and then send a HUP or restart a process. So you can basically get a closed loop watcher that's looking for configuration to change in Consul, renders out a configuration file, and then restarts a service or sends it a HUP, or whatever sort of action you want to get your service to reload its configuration. And that's a very, very common glue into existing applications, is to just render its config files directly from Consul using one of these tools and have it get restarted when things change.
And similarly with the initial start, we need to run the template to generate the config file. Then it's safe for me to start my application and it'll just read the config file.
Exactly. Or you can use the Consul template process to generate that initial config and then restart the service, or let it start the first time. There's other Consul actually has the concept of watches too, so you can register a script with Consul and say when anything changes with this service, or when a node is added, or when somebody touches this key, run this script and pass the information in as basically JSON on standard in. So there's the capability to have sort of a reactive script. That's another way to get at this information in an application that otherwise doesn't know much about Consul. And there's some pretty cool, Mitchell wrote a thing called Consul structure, which is a Go library that lets you basically get a magical map that's driven by stuff in Consul, sort of piped directly into the brain of your Go application. So there's different levels of integration, but it's super common to use DNS and something like Consul template to talk to an application that doesn't have any knowledge of Consul at all.
Okay. Yeah, that I can see how that would be really helpful. For the record, when you speak of Mitchell, you're speaking of Mitchell Hashimoto, whom we talked to earlier on the show about Vagrant, if people want to go and check that out. I wanted to ask another one of these turtles questions in terms of, so we've got a cluster of servers, 3 or 5 servers. How do they start out and find each other? Is that another example of just kind of some seed knowledge that's necessary?
They actually use the same underlying cluster join mechanism that's based on serve, but the member information for a server says it's a server, and when you have an existing server that sees a new one join, it adds it to quorum, to the raft quorum, and starts off basically there's kind of like a parallel process to start up the consensus algorithm, but it's based on the same event of, hey, this node just joined and it's a server. So you generally have to, you generally want to run multiple servers. Consul lets you, for like a completely new cluster, there's a configuration called Bootstrap Expect that lets you say, hey, there's going to be 3. So as soon as you see 3, start up Raft and start going. Once you have a cluster that's already running, it's also easy to add more servers. So if you wanted to go from like a 3 server to a 5 server configuration, you can just do that on the fly. And there's a process for reducing it as well. So, but in terms of your experience as a Consul user, the way you join it to the cluster is very similar. You're just joining an agent that's running in server mode.
Okay. Something you mentioned earlier, Hoshi Corp has a service called Atlas, and I believe it has both a free and a paid for tier. And I think of it sort of as a unification of a number of HashiCorp tools. Can you tell us a little bit more about Atlas?
Yeah, so Atlas is basically HashiCorp's paid set of workflow tools that's built on top of our open source pieces. So we've got a suite of products. Consul Enterprise is one of them. The other 2 are Terraform Enterprise and Vault Enterprise. And so there's a web-based component to those that lets you manage users. Like in the case of Terraform, you can see a change that's going to be made to the infrastructure, have it reviewed by somebody, they can apply it. There's like kind of the workflow layer is provided by Atlas. In Consul's case, there's a free piece of it called Atlas Auto Join. And what this lets you do is solve that initial turtle problem of you let Atlas be the turtle 0 at the base there. So when you bring a new node up in your cluster, you can say, here's my cluster name, here's my Atlas token, I want to join, and it'll give you some addresses to join your node to the cluster. So it avoids you having to manage like a fixed list of servers or fixed IP list for that initial bootstrap. And then the paid portion of Consul Enterprise gets you features like a richer key value editing interface that lets you have organizational permissions for different parts of your key store, and an interface through Atlas to view and edit those, and an alerts feature. So you can take Consul's health checking information and have those events feed into systems like Slack, PagerDuty, HipChat. So you get a hosted solution that lets you bridge onto those escalation services and notification services directly from Consul.
Okay, so not to sound dismissive, but sort of a typical open source strategy of most of the tooling is open source and you can run it yourself. But when you get into enterprise situations where they want things like you mentioned, access control lists and other complexities, that's where the paid for service comes in.
That's right. So yeah, it's sort of like the management, the workflow, the auditing, like those types of pieces are what Atlas provides, and it's working in concert with Consul, which has an open source, an open source component. You could build a PagerDuty escalator thing yourself, or you could use Atlas, that type of strategy.
Right. Okay. Makes perfect sense. So as we wrap up, is there anything else you'd like to tell our audience about Consul or service discovery? I mean, I'm sure it's a huge topic.
There's kind of a pair of features that I think is worth mentioning that's pretty unique to Consul. So we mentioned that as part of sort of the underlying surf mechanism that underpins Consul, you have nodes randomly probing each other at periodic intervals to determine if the node is still healthy. And that feeds into the catalog. So if a node has, if a node's not reachable at the surf layer, then it'll, after a few confirmations, that node will be declared dead, and those services that were on that node won't be given out as healthy services to other nodes. That's kind of the basic bread and butter capability of what those random probes are for. A neat sort of side effect of that is that you're basically getting kind of a randomized sample of the round trip time on your network between all your nodes in basically an automated fashion all the time. So in Consul 06, we implemented a network coordinate subsystem, which uses a set of techniques around, it's basically a set of tomography techniques, which is trying to measure sort of the dimensions of something by measurements from the ends. But what Consul does is as it's doing those probes, it feeds those round trip time measurements into a physics simulation, which ends up creating a set of coordinates for all the nodes in your network. And those coordinates can be used to calculate the round trip time between any two nodes. So you get sort of an automatic model of your network that lets you make interesting decisions about it. So sort of building on top of that, one thing we didn't talk a lot about is that Consul lets you also join different sets of Consul servers together in what we call the Consul WAN configuration. So you can have a Consul in Europe and a Consul on the East Coast of the United States and a cluster in Asia, and those server clusters can know about each other, and you could discover services from one data center in another one. And what's interesting is that the network tomography model can feed into that in a very automatic way. So we have the sort of second feature I want to talk about is something called prepared queries. So in Consul, you can define, you can look up a service locally. You can also define something called a prepared query, which can have a policy like, if there are none locally, give me an instance, try the next 3 closest data centers by round trip time and see if you can find an instance in any of those. And that can all be done automatically with network tomography. So you can, by defining a very, very simple, like a 3-line JSON thing and registering a prepared query, you can basically enable something like geo failover. And if your client's using the DNS interface, you wouldn't even have to change your clients. So it's pretty awesome. Like you can say, here, if I can't find a read replica here, just try the next 3 data centers, and Consul, by maintaining that tomography information, will be able to calculate, well, if it's failing in, if it's in San Francisco, I'm going to try the Asia one, but if it's on the East Coast, I'm going to fail over to Europe. And Consul will manage that architecture on its own. And if a data center goes offline, you'll get the next closest one after that. All that can be managed and expressed in a really, really simple way as a DNS query that your application does, which is pretty unique when all the sort of pieces of Consul come together like that.
That really kind of drives home what you were talking about earlier about other tools and having different pieces of the puzzle and layers and whatnot. I can see, we stack up enough turtles and we have a fairly awesome kind of functionality there.
Yeah. And my only other sort of thought was it's definitely, I would encourage people to run the agent and experiment with it. The agent on its own can do some basic health checking without you really configuring anything. And that's a good way to get a little experience with how it works before you've actually tied it to anything critical in your application. And the things like the network tomography can give you some neat information basically without doing anything, without creating a bunch of network load or a lot of risk. And then you can sort of build on other features over time. But it's pretty easy to get started.
Okay. So how can people follow you, Consul, or the other open source projects from Hoshi Corp? Anything you give us, we can put into the show notes, so you don't need to spell out URLs or anything. But
sure. I'm Slackpad pretty much everywhere. So Twitter and GitHub. The Hoshi Corp Twitter account at Hoshi Corp is good for getting our latest blog posts and announcements, things like that. It's also Hoshi Corp on GitHub. Most of our open source projects are hosted under there. Some still live under Mitchell Hashimoto. We're trying to get a pretty regular cadence of webinars going, so you can definitely watch for those. Or there's a lot of information on YouTube from past webinars and conference presentations, things like that. We have 2 conferences as well. We have an upcoming HashiConf EU in Amsterdam and HashiConf US in Napa, California. So there's some ways to get kind of FaceTime with the HashiCorp engineers through those. And there's a ton of sort of open presentations, things like that. So there's lots of ways to find out about the company.
All right, that's great. Thanks for your time, James. I've really enjoyed our discussion, and I hope our listeners have too. This is Charles Anderson for Software Engineering Radio. Thanks. Bye.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE Radio, or search for the Software Engineering Radio Group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.